Good morning. In this video I'd like to see if I can give you an idea of how the Planck spectrum is modeled. The goals of the video, we want to compare and understand Rayleigh-Jean's law, Wien's approximation, and Planck's law. We also want to locate the peak of the Planck distribution, to understand Wien's displacement law and find the total power and see if it isn't sigma t to the fourth, which would be Stefan Boltzmann's law. So I'm learning something about this as I go. You see this table isn't entirely filled in, but the key is that they called a Rayleigh-Jean's law the classical distribution, and in it all the available energy states are filled. The problem is, as you go to smaller and smaller wavelengths, the number of energy states that are available becomes infinite, and you get what's called the ultraviolet catastrophe. But in the Planck distribution, these energy states are there, but they aren't necessarily filled. Now I'm going to come back in here and change this to momentum states, because I think that is a more accurate word for this. Well, which is it, seriously? Is it energy or momentum? The quantity of interest is called h nu, E equals h nu. I think the reason I'm getting them confused is because when we're talking about particles with mass, it is always going to be the momentum that comes into play with Planck's law. But when you're dealing with light, the photons have zero rest mass, so it really doesn't matter if you discuss things in terms of energy or in terms of momentum or energy. But in this case, we'll see that we're dealing with E equals h nu, which is kilogram meters squared per second times the nu is 1 over second, so it'll be kilogram meters squared per second squared. That is the same as a 1 kilogram. This would be 6.62 times 10 to the negative fourth e negative 4 negative 34, which is the same as 6.62 times 10 to the negative 34th negative 34th joules. Okay, what's the other aspect of this? We're going to be comparing that energy of a photon to the energy associated with the temperature, E equals kT. Okay, what's the other aspect of this? We're going to be comparing this energy associated with a photon with the energy associated with the temperature, kT, where K is called Boltzmann's constant, and it's 1.38 times 10 to the negative 23rd joules per Kelvin. Okay, let's take a moment to look at the three distributions: Rayleigh-Jean's law, Wien's law, and Planck's model of these things. Rayleigh-Jean's law says 2 nu squared kT over c squared was figured simply by counting up the number of states available. I'll describe that later. Assuming that a given region of space would hold standing waves, but it only matched the low frequency part of the graph. The low frequency part of the graph is over here in the high wavelength part. So Rayleigh-Jean's law just kind of came down like, oh, I can't even draw it. Okay, Rayleigh-Jean's law just kind of came up like this. I can't. Come on. Careful. Oh, man. It just came down just like that, and it went up. I missed the arrow. It just went up towards infinity there, so it would have gone up forever towards the ultraviolet. But it only matched the low frequency part of the graph. Now, Wien's law was entirely empirical. It was based on so meaning they had already found this spectral data showing showing this curve, and he just found an equation that matched this part of it that would come up like this, and then would just kind of go up like that. And that is the, I shouldn't call it Wien's law, I should call it Wien's approximation. So I'm going to come back to this table because I'm pretty sure this was empirical here. Because he had the spectrum data and he just wrote an equation to match the high frequency part. And the result was the Rayleigh-Jeans law matched the low frequency part, and the Wien's approximation matched the high frequency part. But the Planck distribution is going to have correct modeling of the entire thermal distribution. So for a moment, let's look a little deeper into how Rayleigh-Jeans, that's actually probably two people and inaccurate that they worked together that closely, maybe, but I don't know. Anyway, it modeled how they modeled the low frequency part of the spectrum. Imagine, if you will, a 1 meter box. Okay. Inside the box, you will find electromagnetic waves, but the waves have a limitation. They must have a node at each end of the box. So you can have that wave, or you can have that wave, or you can have that wave, but you can't have, say, that wave. You can't have quarter waves or anything other than 1/2, 1, 3/2 wavelengths. So you're limited to having some quantized number of waves, 1, 2, 3, 4, 5 half wavelengths, etc. Now, if you want to get into the specifics of this, it kind of falls apart. For instance, if I look at a fireplace and the sun could fit a lot longer wavelengths. However, when we get into these longer wavelengths or larger bodies, when we get into those larger bodies, such as the sun or a fireplace, it hardly matters for our purposes. The sun and the fireplace emit light with wavelengths on the order of millimeters and micrometers. So long as the object is sufficiently large to encompass a few millimeters or micrometers, we can construct our little hypothetical box, and we can make our little hypothetical box and make this weird arbitrary restriction regarding the wavelengths inside it. Okay, if you insist, I will acknowledge that there's something fishy. Of course, there's no reason to say that there are little regions precisely 1 millimeter wide across the surface of the sun where waves can only have nodes on the edges. But I am playing with a hand that I've been dealt, which is an admittedly imperfect understanding of the details. But there's one saving grace of the explanation. These large wavelength waves occur in such small numbers and such small energies that they really don't contribute much to the total anyway. Okay, let's move on to some kind of conceptual idea that leads to some visualizable results. Here is essentially a wave that is trapped in a two-dimensional box. It is the largest form that can be constructed of sinusoids, sinusoids, and be zero at all the edges. See how oops, I'm looking at the inner side. See, it comes down to exactly zero around the edges. Let's see now as I change one of the wavelengths from 2 units to 1 unit. You see there are now 2 antinodes right there and right there inside the box, but the region around the edges is still 0. Now I can change this to any simple fraction with a 2 on the top. Hold on. 2 over 2, 2 over 3, 2 over 4, 2 over 5, and I getting different numbers of waves in the y direction. Now I'll turn it so that Now let's see what we get when we change the number of wavelengths in the x direction. 2 over 2, 2 over 3, 2 over 4, and 2 over 5. You can see that there are a number of unique standing wave patterns available. So you can see that there are a number of unique standing wave patterns available, but some of these patterns have the same or very close to the same energy. For instance, this one with 1, 2, 3 lobes going this way, and this one with very symmetrical but just in the other direction. There's some that are very similar, like this 32 and this 34 have very similar amounts of energy in them. You can imagine if all of those energy states were available, you'd first fill in the lowest energy state, 1, 1, and then the next states, the 1, 2, and the 2, 1, and then maybe the 2, 2, and then the 1, 3, and the 3, 1. And then the more energy states would fill in as more energy became available. And eventually, you'd start to see something that looks kind of like a circle. Or not an exact circle, but something more and more approaching a circle. If we look at that in 3 dimensions, we'd see a sphere filling in, with the center of the sphere representing that state of extremely long wavelength, and the outer edge of the sphere representing all of the extremely short wavelength states. The trouble was when the Rayleigh-Jeans law was written, they saw no reason for there to be a minimum wavelength. So there was no particular reason to stop building onto the sphere, pushing in more and more light of lower and lower wavelengths, lower wavelengths, and which is higher frequency. So someone called this the ultraviolet catastrophe. Who did that? The term ultraviolet catastrophe was first used in 1911 by Paul Ehrenfest. I don't think it's really so much a catastrophe as a modeling limitation. For example, in physics, we regularly say the gravitational field is 9.8 newtons per kilogram, but if you move 1,000 kilometers above the Earth, the acceleration due to gravity is not quite 9.8 meters per second squared. But I wouldn't call this a catastrophe, though. I would just say that my approximation only works within a few kilometers of the surface of the Earth. If I want to model the physics further from the Earth, I will have to use a more sophisticated equation. Okay, so now I've gone ahead and plugged these 3 equations into Mathematica. You can see I want to get some graphs of these things. You can see I have given 3 functions, names Rj for the Rayleigh-Jeans law, W for Wien's approximation, and P for Planck's distribution. I'm going to enter the values of C, H, and K using SI units. C is about 3 times 10 to the 8th meters per second. H is 6.63 times 10 to the negative 34th joule seconds. And K is 1.38 times 10 to the negative 23rd joules per Kelvin. For now, I will plug in the temperature of the sun, which is around 6,000 Kelvin. And I know the sun has a peak wavelength somewhere around 400 to 700 nanometers, which kind of makes me wish I had used the wavelength distribution rather than the frequency distributions. However, I think I may have an easy fix. The relationship between wavelength and frequency is frequency times wavelength equals the speed of light. So all I have to do is solve that for frequency as a function of wavelength, getting frequency is equal to c over lambda. So I'm going to put that into each of these, c divided by lambda. So it will still plug the frequency into each of the equations, but I can work conceptually with the wavelengths and put the wavelength on the axis. So here I can put limits on my plot domain of 400 to 700 nanometers. After a couple of corrections, this is what it looks like. I'm pretty sure that this is Rayleigh-Jean's law dominating the graph with its ultraviolet catastrophe, while Wien's law and Planck's law cannot be distinguished at this scale. So I'm going to remove this one, or comment it out, and see what the graph looks like. Now, for some reason the gray line has disappeared. Okay, I see. Mathematics defaults to drawing a blue line, then a purple line, then a gray line. What we have now is it's drawn the blue line and then it drew the purple line right on top of each other so that they can barely be distinguished. What I need to do on this is to increase the range on this to higher wavelengths where Wien's law will differ from Planck's law. So I'll put in, say, 2000 nanometers and see what comes up then. Ooh, wait, it's still very, very close. Why is that? Nope, I was wrong. Graphing my equation for Wien's law and Planck's law separately, I can now see that there is an alarming separation of scale. This one is 10 to the negative 22nd, this one is 10 to the negative 8th. Looking now, I see that the blue line is actually down here, hidden behind the x-axis. Most likely the reason for this discrepancy is that I made a typo right here in Wien's approximation. It should have been nu to the cubed instead of nu to the squared. Excellent. Now we can see that Wien's law is very close match at shorter wavelengths, but it misses the mark at larger wavelengths. Here now we see all three plots together, the Rayleigh-Jean's law in blue, Planck's law in gray or brown, and Wien's law in purple. Now, if I understand correctly, Wien's law was almost entirely empirical. His goal was just to find an equation to match the data. He played around with the math until he got an equation, and he really didn't try to explain exactly why it worked. On the other hand, Planck works with something either called Bose-Einstein statistics or Fermi-Dirac statistics. It must have been Bose-Einstein statistics since photons are a type of boson, not a type of fermion. This equation could represent any boson, like superfluid helium or such weird substance. We're more concerned with photons for the moment, for which chemical potential doesn't really mean much, and so we would replace this with essentially G sub I over, boy, I can't get it to write. So we would replace this epsilon I minus mu with an H nu over kT. And that G sub I is associated with the degeneracy, which is a word that physicists use when they mean that many different wave functions have similar or identical values for energy. Now, I don't quite currently remember how these probabilities are worked out, but suffice it to say, between Fermi-Dirac and Einstein and Bose, they figured out a way to assess the probability that an available energy state would be filled, and then Planck used those probabilities with the Rayleigh-Jean's law to create an exact prediction of the thermal spectrum. I tend to think of Bose-Einstein statistics kind of like dice, where there is no particular reason why two bosons cannot share the same energy state. While I think of Fermi-Dirac statistics more like cards, where if you have two cards with the same value, it probably means someone is cheating. Now there was one more thing I wanted to do with this distribution, which was to integrate it and see if we didn't get something resembling a sigma t to the fourth. On my first little attempt integrating with frequencies between 0 and infinity, of course I got an error. So let's try preserving the essence of the equation by setting all of the constants to 1 and then just integrating x cubed over e to the x minus 1, and we get pi to the fourth over 15. Okay, even better. Mathematics seems to handle things perfectly well if we put all of the undetermined constants in there, showing that so long as h over kt is greater than 0, is a real number greater than 0, we get a quantity which is constant times t to the fourth. So when we integrate that, we get 2k to the fourth pi to the fourth t to the fourth 15 c squared h cubed. Now, for some reason, which I do not currently know, this needs to be multiplied by a further factor of pi to get what is commonly known as which is currently referred to as sigma, or Stefan-Boltzmann's constant, 5.67 times 10 to the negative 8th joule Kelvin per meter squared second. And I guess that wraps up things for now. Thank you for watching.